Welcome to a new episode of AI Research Radar, where we showcase the most cutting-edge developments in the field of artificial intelligence. Join us as we shine a spotlight on the latest advancements and breakthroughs in AI research. From machine learning to natural language processing, AI Research Radar covers it all to keep you informed on the forefront of AI innovation.
The paper. Toward self-improvement of LLMs via imagination, searching, and criticizing. Introduces Alpha LLM, a novel framework for self-improvement of large language models, LLMs, that integrates Monte Carlo tree search, MCTS, with LLMs. The framework is composed of three key components. Data synthesizing. This component is responsible for generating synthetic prompts as learning examples. The generation of each synthetic prompt is a transformation applied to one or more examples from the initial dataset. The transformation function can be a learnable function, manually defined heuristic rules, a strong LLM, or the policy model itself equipped with data synthesis instructions. MCTS, efficient MCTS. This component is designed for efficient searching in language tasks. It uses an option-level MCTS where each option represents a sequence of tokens. The option-level MCTS includes for operations, selection, expansion, simulation, and backpropagation. It also introduces techniques like importance-weighted expansion and state merge to enhance search efficiency. Critic models. These models provide precise feedback to guide the MCTS. They include a value function for estimating future rewards, a process reward model for assessing node correctness, and an outcome reward model for evaluating the overall trajectory. The framework also includes a policy self-improvement process that iteratively refines the policy model by learning from synthesized prompts and corresponding responses obtained using MCTS. The refinement process includes two main steps: data generation and policy fine-tuning. The authors conducted experiments on mathematical reasoning problems to validate the effectiveness of the Alpha LLM framework. They used two widely used datasets for this purpose, GSM-8K and Math. GSM-8K, this dataset was used in its entirety for testing. Math, due to computational constraints, a subset of this dataset was used, following the same procedure as in a previous study. The performance of the models was evaluated based on their ability to predict answers correctly. The average number of rollouts, represented by the number of nodes in the tree, was also calculated as a measure of computational efficiency. The performance of Alpha LLM was compared against a suite of proprietary models, including OpenAI's GPT-4 and GPT-3.5, Anthropic's Claude 2, Google's Palm 2, and the Gemini model family. They also conducted comparisons with strong open-source models, including Llama 270B and WizardMath 70B. The authors selected Llama 270B as the policy model for the GSM-8K dataset and WizardMath 70B v10 for the math dataset. They constructed the training dataset for the value function, PRM, and ORM by generating 50 trajectories for each prompt and constructing the training target following the methods described in the paper. The experimental results demonstrated that Alpha LLM significantly enhances the performance of LLMs without requiring extra data annotations. Moreover, when decoded with MCTS, Alpha LLM performs comparably to GPT-4, highlighting the potential for self-improvement in LLMs. The authors conducted an ablation study to assess the effectiveness of each component in Alpha LLM. They found that each component of the framework contributed to the overall performance improvement. The most significant improvement was observed when the ORM with fast rollout was introduced. In conclusion, the experimental work conducted by the authors validated the effectiveness of the Alpha LLM framework in improving the performance of LLMs on mathematical reasoning tasks.
This is AI Research Radar. Now, we will be delving into the next paper on our agenda.
The paper titled Automated Social Science, Language Models as Scientists and Subjects presents an innovative approach for automatically generating and testing social scientific hypotheses using large language models, LLMs, and structural causal models, SCMs. The key methods used are as follows. Structural causal models, SCMs. SCMs are mathematical models that represent cause and effect relationships. They are used to state hypotheses, construct LLM-based agents, design experiments, and plan data analysis. SCMs serve as the backbone of the research process, enabling the automation of hypothesis generation and testing. Large language models, LLMs simulate human subjects in experiments. They are capable of generating hypotheses, designing experiments, running these experiments on independent LLM-powered agents, and analyzing the results. Automated hypothesis generation and testing. The system begins by selecting a study domain. It identifies potential outcomes and causes that might influence these outcomes. These variables and their proposed relationships form the hypotheses. The system designs an experiment to test these hypotheses by inducing variation in the causes and measuring the outcomes. After designing the experiment, the system determines how it will analyze the data in a pre-analysis plan. It then recruits participants, runs the experiment, and collects the data. Finally, it analyzes the data per the pre-analysis plan to estimate the relationships between the proposed causes and outcomes. Open source computational system. The authors developed an open source computational system that implements this SCM-based approach. The system can automatically generate hypotheses, design experiments, run these experiments on independent LLM-powered agents, and analyze the results. Interaction protocols. The authors designed 6 interaction protocols to determine the speaking order of agents in the simulations. These protocols include ordered, random, central random, coordinator before, and coordinator after protocols. Post-simulation survey and data collection. After the experiment, the system conducts a post-experiment survey to measure the outcome variable in each simulation. The system then takes this question's raw answer and saves it as an observation along with the values of the exogenous variables. Path estimation and model fit. With a complete dataset and the proposed SCM, the system can estimate the linear SCM without further queries to an LLM. The system uses the R package Lavaan to estimate all paths in the model. The authors conducted several experiments to validate their approach of using LLMs and SCMs for automated social science. They used a computational system they built, which uses LLMs to generate and test social scientific hypotheses automatically. The system was designed to mirror the experimental social scientific process, including hypothesis generation, experiment design, data collection, and analysis. The experiments conducted involved various social scenarios, including 2 people bargaining over a mug. The system proposed hypotheses about the factors that could influence whether a deal occurs, such as the buyer's budget, the seller's minimum acceptable price, and the seller's emotional attachment to the mug. The system then ran simulations of the bargaining scenario, varying these factors to test their effects. A judge setting bail for a criminal defendant. The system proposed that the defendant's criminal history, the number of cases the judge has heard that day, and the defendant's level of remorse could influence the bail amount. Again, the system ran simulations, varying these factors to test their effects. A person interviewing for a job as a lawyer. The authors manually selected the hypotheses for this scenario, including whether the applicant passed the bar exam, the interview's friendliness, and the applicant's height. The system then ran simulations, varying these factors. An auction for a piece of art. The authors manually selected the hypotheses, including each bidder's maximum budget. The system ran simulations of the auction, varying these factors. The results of these experiments were then compared to theoretical predictions and the predictions of the LLMs themselves. The authors found that the system's simulations produced results that were highly consistent with theoretical predictions. They also found that the LLMs were not able to accurately predict the outcomes of the simulations without the fitted SCMs, suggesting that the simulations were able to elicit information from the LLMs that was not available through direct elicitation.
This is AI Research Radar. Now, we will be delving into the next paper on our agenda.
The paper titled ACTIVERAG, Revealing the Treasures of Knowledge via Active Learning, presents a new framework called ACTIVERAG, Retrieval Augmented Generation, that aims to improve the learning and comprehension capabilities of large language models, LLMs. The framework introduces an active learning mechanism that shifts from passive knowledge acquisition to active knowledge construction. The methods used in this framework are knowledge construction. this approach uses the knowledge construction mechanism to develop a deeper understanding of external knowledge by associating it with previously acquired or memorized knowledge. It involves four distinct agents dedicated to knowledge construction. Semantic association. This encourages the model to integrate familiar information and foster a deeper understanding through the consolidation of foundational and advanced understandings and knowledge through experience and social discourse. Epistemic anchoring. This pertains to unfamiliar knowledge and focuses on representing information previously unknown to the model. Logical reasoning. This leverages structured information to draw logical conclusions and refine the model's problem-solving capabilities. Cognitive alignment. This deals with knowledge that may contradict the model's pre-existing understanding, preventing factual errors and mitigating the hallucination of LLMs. Cognitive nexus. Following the constructivism learning theory, the cognitive nexus mechanism is utilized to connect external knowledge with the inherent cognition of LLMs. It first generates an initial chain of thought, COT, for problem solving and subsequently leverages the outcomes of knowledge construction to refine the COT, thereby producing more precise answers. Retrieval-augmented generation (RAG) models. Given a query, existing retrieval-augmented generation (RAG) models utilize retrieval models to search passages and enhance the generation ability of language models by grounding these retrieved passages. ACTIVERAG enhances the active learning capability of LLMs without necessitating further fine-tuning and employs a three-step pipeline to construct the RAG model, including retrieval, knowledge construction, and cognition nexus stages. The methods used in ACTIVERAG are designed to improve the learning and comprehension capabilities of LLMs by actively constructing knowledge from retrieved passages and integrating it with the model's inherent cognition. The experimental work used to validate the methods in the paper ACTIVERAG, Revealing the Treasures of Knowledge via Active Learning, involved several steps. Dataset selection. The authors used 4 datasets for open domain question answering to evaluate the performance of ACTIVERAG. These datasets included natural questions, NQ, PopQA, Trivia QA, and WebQ. They randomly sampled a subset of 500 questions from each QA dataset for their experiments. Evaluation metrics. The authors used accuracy, ACC, to evaluate the performance of different models in open domain QA. They converted both the outputs of the LLM and golden answers to lowercase and subsequently performed string matching between each golden answer and the model prediction to calculate the accuracy. Baseline models. The authors compared ACTIVERAG with several baseline models, including prompt learning and RAG models. All prompt templates used by baselines were shown in the appendix. Implementation details. The authors accessed GPT models via the OpenAI API to evaluate the performance of the ACTIVERAG. They employed GPT 3.5 Turbo's 1106 as the foundation model for inference and set the temperature at 0.2 during the generation. They used T5FANCE to retrieve top K relevant documents from Kilt Wikipedia for each question. Overall performance. The authors compared the performance of ACTIVERAG with all baseline models across all datasets. They found that ACTIVERAG surpassed all baseline models, achieving a 5% improvement. Ablation study. The authors conducted ablation studies to demonstrate the effectiveness of the cognitive nexus method by integrating different knowledge construction methods with the chain of thought. Characteristics of different knowledge construction mechanisms. The authors conducted experiments to show the characteristics of the associate-based knowledge construction method. Generalization ability of knowledge construction outcomes. The authors showed the quality of the knowledge construction outcomes using different LLMs. They leveraged the outcomes of ACTIVERAG to prompt weaker LLMs, specifically Llama 2-7b, 13b, for answer generation. Case studies. Finally, the authors provided case studies to illustrate the effectiveness of ACTIVERAG in supporting LLMs to combine both external knowledge and intrinsic cognition for answer generation.
Thank you for joining us for this episode of AI Research Radar. Be sure to stay tuned for our next episode where we will showcase the latest innovations in AI research. If you enjoyed the content, please consider subscribing and liking the video.